It is 1633, and inside the cold stone chambers of the Roman Inquisition, a 69-year-old mathematician kneels before the most powerful tribunal in Europe. He stands accused of holding and defending a dangerous idea, that the earth moves and the sun sits motionless at the center of the universe. It begs a practical question. How did an elderly scholar, armed with nothing but glass lenses and mathematical calculations, become a mortal threat to the continent's ultimate authority? For centuries, the structure of the cosmos was a settled matter. Absolute truth flowed from religious doctrine and ancient texts, specifically the physics of Aristotle and the astronomy of Ptolemy. According to this deeply entrenched worldview, the Earth was fixed at the center of a perfect, unchanging universe. To challenge this Earth-centric model meant contradicting the literal interpretation of Scripture. Questioning the physics of the ancients meant questioning the intellectual foundation of the Church itself, threatening the social and religious order of the 17th century. Decades before his trial, Galileo Galilei had built a reputation as a relentless tinkerer. While other scholars debated the nuances of ancient philosophy in university halls, Galileo preferred to test physical reality directly. Aristotle had stated that heavy objects fall faster than lighter ones. To test this, Galileo is famously said to have dropped two spheres of similar size, one made of lead, the other of cork, from the Leaning Tower of Pisa. By isolating the variables, he found they fell at the same rate, proving that mass alone does not dictate the speed of a falling object. Because free-falling objects moved too fast for the timekeeping tools of the era, he designed a way to slow gravity down. By rolling a bronze ball down a smooth wooden ramp, he timed its descent. He found that distance traveled in successive intervals increased by odd numbers, 1, 3, 5, 7. The total distance covered equaled the square of the time elapsed. The motion followed a strict mathematical formula. These resulting laws of motion provided something the ancient texts lacked, a predictable mathematical description of how objects actually behave. For the first time, physical measurement had replaced abstract logic as the primary tool for defining the rules of motion. In 1609, Galileo learned of a Dutch device that magnified distant objects. He refined the design, grinding his own lenses to build an instrument capable of magnifying 20 times, and pointed it at the night sky. The prevailing belief dictated that all celestial bodies were perfect, unblemished spheres. Yet when Galileo looked at the moon, he observed jagged shadows extending across its surface, revealing deep chasms and vast mountain ranges. Turning his lens to the Milky Way, he saw that the glowing celestial cloud was actually composed of thousands of individual stars, entirely invisible to the naked eye. He then tracked the planet Venus. Over several months, he observed the changing light on its surface. He saw Venus pass through a full cycle of phases, from crescent to full, exactly like the moon. This geometry is only possible if Venus circles the sun, contradicting the geocentric model. Finally, he observed 4 moons orbiting Jupiter. It was undeniable proof of multiple centers of rotation in the solar system. Taken together, these physical observations dismantled the Aristotelian cosmos piece by piece. The heavens were not perfect, and the Earth was not the center of all celestial motion. In March 1610, Galileo published these findings in a short treatise titled Sidereus Nuncius, or The Starry Messenger. The evidence supporting the Copernican model immediately brought him under intense scrutiny from religious authorities. By 1616, a panel of theologians for the Roman Inquisition formally declared the heliocentric theory to be heretical. Galileo was directly ordered to abandon the doctrine and abstain from teaching or defending it. He remained largely silent on the issue for over a decade. But in 1632, believing he had the support of the new Pope, Urban VIII, he published the Dialogue concerning the two chief world systems. The book was structured as a conversation between 3 characters. The character defending the Copernican view systematically dismantled the arguments for a stationary Earth. Those geocentric arguments were placed in the mouth of a character Galileo named Simplicio, which had the contemporary connotation of simpleton. By mocking the intellect of the papacy in print, Galileo turned a theological debate over the cosmos into a direct political insult. The Pope withdrew his protection, and the Inquisition summoned the astronomer to Rome. This brings us back to the stone chambers of 1633. Interrogated and threatened with physical torture, the tribunal found him vehemently suspect of heresy for holding that the sun lies motionless at the center of the universe. To avoid execution, the aging scientist was forced to kneel before the tribunals, publicly abjure his findings, and curse the very concepts he had spent his life proving. He abandoned the physical truth to save his own life. Legend states that as he rose from his knees, he muttered a final, defiant phrase under his breath, and yet it moves. The Inquisition's sentence was absolute. His dialogue was immediately banned, along with any future works he might attempt to write, and he was confined to strict house arrest for the remainder of his life. The Church successfully isolated the man, but the physical copies of his research, filled with undeniable astronomical data, were already circulating freely across Europe, far beyond the Inquisition's reach. Even in his confinement and slowly losing his eyesight, Galileo continued to work. He returned to the physics of his youth, compiling a foundational text on kinematics that would provide the mathematical basis for Isaac Newton's laws of physics decades later. By prioritizing physical observation and mathematical verification over established doctrine, Galileo established the core tenets of the modern scientific method. His work transitioned the study of nature from a branch of philosophy into a rigorous system of evidence. An institution can use its power to force a man to his knees and ban his writings. But as Galileo's legacy demonstrates, authority cannot permanently silence the observable mechanics of the natural world.